Perhaps you are like me in that the way you were taught to factor loads was you factor the loads first, then you go about your design. You get into the design office, however, and you get your first assignment, and what do? You start factoring loads first. However, you quickly run into a jam because you realize you can't track your loads all the way through the structure because you've already factored them. Eventually, you figure out that you want to factor the loads last. I'm going to show you the way that I wish I was taught load factoring, and then I'm going to teach you a way to create your own library in Python for factoring loads that will work for both scalars and arrays and you can use for the rest of your career. This is Structural Python. Let's say we have a business that operates in 3 countries, Mexico, Japan, and say France. Therefore, we have business operations in Mexican pesos, Japanese yen, and euros. Each of these businesses are going to have their own set of incomes and expenses. In Mexican pesos, you might have 20 and 30 minus 10 of expenses. In our Japanese operation, 30 plus 45 minus 15 in expenses. And in euros, we seem to have no expenses. We're just adding up revenue. That's great. So once we have these 3 accounts, can we just add these currencies together? We can't, because they are completely different. In order to do this, we need to combine them into a common currency. We multiply each of these currencies by a different factor that is converging into, say, Canadian dollars. This ends up being like our demand in a structural system. We compare our demand, our income and expenses, versus our bank account, our capacity. Since everything is into a common currency, we can compare it directly. Similar with a structural system, we may have our dead, our live, and our snow load. We're going to be accumulating load from the roof, level 3, and level 2 onto one member. Similar with currencies, we maintain separate sets of books to keep track of the dead, live, and snow load, their demands as they accumulate down the building, because we cannot add them directly together. Only by combining them with a factor to convert them into a kind of common currency can we then add those loads together and to create our factored load. Now we have our factored load, we can compare against the capacity of our member, which is in effect like checking to see if we have enough money in our bank account. So the question now is, how do we implement this in Python? Nowadays, I think of working with different load cases as like working with different currencies. Say we had loads on level 2, level 1. We can add up the like loads with like loads. Dead load, live, snow. And we can see the subtotal here printed out. So this idea of factoring allows us to convert to this common currency using this metaphor. And it's easy to calculate one factored load for one calculation. But of course, we need to automate this because we've got many combinations of factored loads. So how can we manage this? One way of doing this is to write separate functions. The pros for this is that you've got one function, one name, and it's easy to write, conceptually simple. But you'll very quickly end up working with repetitive code and also brittle code. An implementation of this could look like this, where you've got each load combination representing one different function. And so the function signatures here are all different depending on the load combination. This is what makes this code brittle, because ideally you want to be able to load all of your loads in and just run through all of the functions to calculate them all at once. But because these inputs are different, you'll end up breaking your code. So to call this function one-off is quite easy, but it can be quite repetitive because you will have to end up calling these one-off at a time. Another approach might be to write a generic function. The idea is to write sort of one function to rule them all. And one way to do this is with using dictionaries to represent both your loads and your load combinations. The idea here is that this function can be extensible because you can change your load combination factors to whatever you want, and you can also change the number of them as you need. However, if you want to use this function manually, it can get quite tedious. So here's an implementation of what this kind of function could look like. We've got inputs for both the factor and the load, and they're all set to a default value of 0. So if one of those factors and loads is not passed to the function, it ends up just not calculating those extra loads, which makes this quite easy to write, especially if you're looping through all of your loads at once. So if we were to call this function manually, it can be quite tedious because you're typing 1.25, 1.5 every time that you're doing this calculation. However, the idea here is to use dictionaries to automate that process for you. So if you've got a dictionary of combinations, you can break out what each load factor is with its label. So you can see that this is the dead load factor, this is the live load factor, this is the snow factor, etc. Additionally, you've got your loads represented by a dictionary also. And so to call this function is now just a matter of unpacking your loads with the keyword argument unpack, and also unpacking your combos dictionary after you've given it a certain combo. So we can run it with combo to B, to A, and combo 1 very quickly. So this is nice because we can see what each of these factors are in relation to which part of the load combination they correspond to. Another approach could be to write a generic function like we did before, but using arrays. Now, the nice part about this is that you don't end up having to write loops for adding your load combinations together. You end up writing just simple code because you're using array math. It can also be quite brittle because you have to manually enter, you have to make sure that your arrays are fixed length. You can't say enter only your dead and your live for a load combination that requires only dead and live. You have to enter all loads with all those extra zeros at the end. I'll show you what I mean by this. So if these are our load combinations, you can see here that I've got all these extra zeros at the end. This is our dead, this is the live, snow, wind, earthquake. However, it's hard to sort of see what these are. You just have to know in advance that that's what these placeholders represent. So if we've got our load combinations and our load also as a vector, we've got this beautiful, easy implementation for the function. Because what we're actually doing is we're going to go through element-wise and multiply each load vector by the factor and then sum the total. This is actually equivalent to doing a matrix multiplication. Now, I'd love to tell you that I recognized that right away, but it didn't. It took me a little bit to realize that I was doing a matrix multiplication and just swapping that out. So here's an example of what it could look like. We have our load vector here, and then we can call the function with our load combination and our load vector. So pass it the combination vector and the load vector. It does the matrix multiplication and gives us our factored load. So if we're going to be storing load combinations, because you don't want to have to write that dictionary of load combinations every single time, there's two ways we could do this. We could either use a dict or a list or an array. So as I was talking about, when you use a dictionary, the nice thing about it is you get these key value pairs. So you can see that D is this load magnitude and the dead load factor is this number. You also don't have to fill in all these extra padded zeros here. You can just pass in the loads that you have that are relevant for that load case or that load combination. The cons for this is that you don't have a vector math, you don't have a way of doing the calculation built in. You have to manually write a loop to add all these numbers together. Versus an array, you've got fast and simple vector math, but you have no labels on your data. You just have numbers that you have to know in advance that that's what each position in the vector represents that load case. And then you also have to make sure that you put in the fixed length vectors. So you have to put in all these padded zeros here to make sure that the vector math actually performs properly. So here's what a factored dictionary could look like. Here's what you could do with it is store it into a JSON file. So this dictionary here hasn't been assigned a variable. You just take your dictionary, put it into a master dictionary, and store it as in JSON text. Then you can load it into a dictionary whenever you need it. Here's an example of what that file looks like here. So you can store this write these load factors ahead of time and store it as part of your factoring library, and you can load it dynamically. Also, you can write these JSON files to work for different codes. So if you're working on a bridge code versus the building code, or you're working on building codes in different countries, then you can write these load combinations in advance and switch codes very quickly. So now we're using our factored loads. We pass in the load factors. And as I said, we don't need to, we can pass in a dictionary, or we can just manually enter them and then provide the load combination from our dictionary that we want to compute. To do it with vector dictionaries, you're still going to write a dictionary that will be your sort of master JSON container, but then you're going to have key value pairs, and the keys are going to be the name of your load case, and the values are going to be your combination vectors. So if you were to load this up into, from a JSON file, you would get a dictionary resulting here that would look like this. And then you can go ahead and call your function to calculate your factored load in a very similar way. You pass in your load vector and your factor vector. So we've got this sort of trade-off: labels on your data versus array math. But there is a third way of doing this where you can have the best of both worlds. You can use the labels from the dictionaries and use array math by using a named tuple to represent your load. Because the named tuple has these fields that contain these labels like dead, live, snow, or dead load factor, live load factor, that sort of thing, it is dictionary-ish. And because it's also a tuple, it can be converted directly into a NumPy array, which is array-ish. Which means that you can skip the empty 0, 0 values when you define your load, because those can be defined as default arguments and fill in the rest of it for you automatically. So what would such a named tuple look like? Here's how I've implemented this. Very simple. Create a load class, and it is going to be a subclass of named tuple. You've got your dead, live, snow, wind, earthquake, all of your load cases here, and they can be of any type. So we can use arrays here in this class, or we can use scalars and just set it to 0, 0 as a default. So if I were to call this with no loads, I would get an empty load where everything is zeros. If I were to just pass dead, live, snow, I would get those three values, but then wind and earthquake would be zeros automatically. And so I could also pass in an array of values for each load combination. So in this case, I've got an array of 3 dead loads. This might represent 3 different locations on a beam, or 3 different reactions, or it might represent 3 different floors. It could be whatever you want. However, when I do arrays, I have to make sure that I pass in these padded zeros here for the load cases that I'm not yet defining. So let's review what this looks like. If you were to print these out, this is what the empty load looks like. This is what the load with just the scalars looks like. And then this is the load with array values. The dead equals that array, live equals that array. So we can treat this as both a dictionary and as a vector. And as a demonstration of this, we will use it for we can use our factored loads function, which is assuming dictionary style input. We can unpack it using the keyword argument unpacking after we've created it as called asDict, is one of the built-in methods on named tuple types. Additionally, we've already defined our load combination dictionary, so we just do the tuple unpacking here. And now we get an array of factored loads. So this is the factored load in, say, the first reaction, the second reaction, and the third reaction. So very convenient. And we can call it as a vector. So instead of doing a dictionary unpacking, we call NumPy array on it to convert it into a NumPy array. For the matrix multiplication to work out properly with the right dimensions, we have to do a transpose of this vector. And then we just turn our load combination into an array as well, and then the matrix math works out with the exact same result. So another thing that can be nice to do as you're building out your factoring library is to have this idea of load aliases. Sometimes when you're doing a design or you're doing an assembly and calculating a dead load, you want to be able to separate, say, your superimposed dead load from your self-weight dead load. And you might even want to be able to break it out more so that you would say that your superimposed dead load is like asphalt topping plus layers of insulation plus layers of tile, I don't know, whatever you'd like. And so to do this, we can create this sort of load aliases. And now these would be personal to you and the way that you work. So if we had a series of different load types that we wanted to sort of represent as with their names, say self-weight is SW and superimposed dead load is SDL, but they are both dead loads, we can create a dictionary that's sort of like a lookup. So that way any load that we've demarcated as self-weight is actually going to be converted to dead load when we do our factorization. Same with planter soil, it could be whatever label you want. Snow and rain, you can break those out separately if you really wanted to, and those would all just be sort of included together as snow load. So how would this kind of a function look? Very simple. You're just going to be looping through your dictionary of loads and then looking up what their values are in your alias lookup dictionary. Then, because you're working with dictionaries, and this is what I was talking about before, is you have to write your own sort of vector math. Is you have to, as you look them up, you then have to add them to your new service loads dictionary. So if the load type is already there, say the dead load, you've already calculated one dead load. Let's say you've done the self-weight already, that's been added to your service loads dictionary. Now you've come to the superimposed dead load. We see that there's a dead load entry already in your service loads. Therefore, if it's already in there, then we need to add the new one to the existing one. Or rather, the new one to the existing one. And then otherwise we just update the dictionary. And then at the end, we convert our service loads accumulator into this load data type. So what does that look like? So we've got our alias lookup table here, and then we've got our loads dictionary. So self-weights, SDL, planter soil, snow, rain, etc. So we call this alias to service loads. We turn this loads dictionary into a loads named tuple. And so we'll see this is what the input is, and then this is what we get as our output, and you can see that the self-weight and SDL have been added together to create 44, and then the snow and the rain have been added together to create 32. So the idea with this whole thing with factoring loads is to find the minimum and maximum. So I think of this as there's two approaches to do it. You can do one, just the most basic, where you just want to get the max and the min, and you can write a function to do that, or you could calculate the max and the min and have the ability to go back and find out which load combination it is that governed in a particular calculation. I prefer having both approaches because there's times when it can be useful to try to trace back what load combination created the governing case, so that way you can hand validate your answers. So in order to do that, we do need to use NumPy for this, which we've been using for our array vectors. So why using NumPy is because if we want to do these element-wise maximums between arrays, we can't just use like the built-in Python greater than, less than symbols. We need to use a function in NumPy called maximum and likewise minimum. The reason for this is because maximum works on both scalar and array inputs, and what it does is it compares two arrays. Let's say your array A, array B, and then it goes through and finds the element-wise maximum of the two arrays. And so if you've got, let's say, a list of 5 arrays that you need to do it, you need to go through, compare 1 to 2, and then the accumulated 1 to 3, and then accumulated 1 to 4, and so on. And in that way, you can build up your envelope of factored loads if you're working across arrays. Because it works with scalars as well, you can just write one function that will work with both arrays and scalars. So let's go with the first approach. We're just returning max and min loads. This is what the function could look like. We're going to start off with like a number accumulator. That's going to be this FL here, our float. And we're going to start off with the smallest possible value. So that way any value that we look at after it is always going to be larger. Don't use 0 for this because your numbers might all be less than 0. They might all be negatives. Use the negative infinity, the smallest number possible in the programming language. So that way every number afterwards is going to be larger. So in other words, we want to say, once you see the first number, take that as the maximum. And that can be done by setting the accumulator as the negative infinity value. So we're just going to go ahead and loop through our load factors and the load combinations. We're going to call our factor vector load, which is going to just take the array of our load case and array of our load factor. It will compute the current maximum, factored load maximum, and then it'll compare it to the existing one or the previous one in the loop. So now we're comparing the previous one in the loop that we've accumulated to the one that we are currently have just calculated, and then we're storing that as our new maximum. And then we're outputting the maximum after this has completed the loop. Same idea with the minimum. except now we're accumulating off of positive infinity, so every number that we look at is going to be smaller than that. And this is how it'll work. So we pass in a load combination vector. So let's say we've passed in L2, which, just a reminder, looks like this. It has an array of 3 values for every load case. We've got dead, live, snow, but no wind and earthquake. Then we pass it our dictionary of load vectors, nbccvec, which looks like this. We pass this load with this whole thing, and then it calculates the max factored for each separate position in the array. Same with the min factored, it calculates the minimum load factor for each position in the array separately. The other approach here is to return the maximum minimum governing combination. So in order to do this, we have 2 steps. We need to build a matrix of all of the calculated load combinations, and then we're going to look for the index, the location of the maximum within that matrix. First, we write a helper function to get the factored matrix. We're going to be looping through all the load combinations. We're going to be accumulating them into an array, and we're going to, every time we loop through it, we're going to concatenate the array to the previous one. Then our max factored now is not going to return the max value. It'll calculate and return the location, the index position within the matrix. And to do that, we're going to use the NumPy array argmax, and we're going to make sure that we want to return it row-wise, so we pass axis equals 0. Same with the minimum. And then, so here's what the returning values look like. So this is our factored matrix here, representing load case 1, load case 2a, 2b, 2c, 3, and however many we had here. Let's look at what we have. So for every one of these load combinations, this is the calculated result. And now we're going to find the position of the maximum. So position 3, 3, 6. So in the first position, 0, 1, 2, 3 maximum, 0, 1, 2, 3 maximum, 0, 1, 2, 3, 4, 5, 6 is the maximum location here. Likewise with the minimum, we can see that we've got 0.84 is the first minimum, 1.54 and 0.56 is the minimum here. So that's what we're getting when we do the factored max trace. Last, we've talked about sort of 2 different abstractions here, this vectors and dictionaries, and we've also talked about load aliases, where you can be able to sort of separate the self-weight and the superimposed dead load. But when working with buildings, it can be convenient to talk about occupancies, where a given occupancy has a certain dead load, live load, and say snow load, or wind or earthquake. It's got some of its own unique combination. Dictionaries are useful for organizing these. So this is what an occupancy dictionary might look like. You might say residential has a self-weight here, a superimposed dead load here, and a live load here. Residential roof might be broken down this way, an amenity roof might be broken down this way, and rooftop mechanical might be its own thing. And so by using our alias lookup, we can then convert this. We can just say, I want the occupancy to be residential roof. We run it through our alias lookup function, and then we factor it. And then we can just say, this is the factored load for that occupancy. Here is what the service loads for that occupancy end up as, and here's what the factored value is. So if we were to use occupancy vectors, we could do it a little bit differently. We don't have the flexibility to do these alias lookups with our factors the same way we do if we were using a dictionary. So if we used an occupancy dictionary that was built on vectors, you'd want to calculate these dead load, live load, snow, wind, earthquake, calculate those all separately and store each one as an array in your dictionary. Last, I want to get into a practical example here. We're going to have a simply supported beam with one UDL, one point load. We're going to use the pycba analysis engine by Colin Caprani. Let's load in our load combinations, and we're going to create our beam here. We're going to have 2 nodes, 2 vertical reactions, length of 6.9 meters. These are our loads here for our distributed load. This is the load for our point load, and this is the distance from our point load from the left end of the beam, and we're not really worried about an EI right now because we're just looking at moments, shears, and reactions. So to process this beam with all of these load cases, like many open source libraries that do beam analysis, we have to manage our load cases ourselves. So create a dictionary as an accumulator where you're going to store your dead load analysis, your live load analysis, snow, wind, etc. Once we've got these beam results, we have to do a bit of post-processing here. We're going to separate out our reaction results on the left. We're going to put all of those scalar values into an array here to be unpacked into our load NamedTuple data type. Same for the reaction on the right, the moment array, the moment results array, and also the shear result array. Now that we've got these arrays broken out, we can calculate our factored loads. When we got the max of the moment results using this combination dictionary, and the minimum of the moment results using this combination dictionary for the shear, for the left reaction, and the right reaction. Because I mentioned, now our factoring max and min functions work for either scalar or array value, so we can calculate the reactions the same way we calculate the moment and shear arrays. Let's look at what the results look like as force diagrams. Here is the moment envelope showing the max moment and the min moment. Same with the shear envelope. Now I'm hoping you can start to see some of the power of this approach. I've encoded this into a Streamlit application, which I've included a link to in the description. You can go through and try altering the loads on this beam and see exactly which load combinations govern and how they fit within the envelope. Last, I wanted to say that there's a GitHub repository that I've created that has all of these libraries in it. It has the notebook that you've been watching, it has the resulting factored load library that I use myself with my load combinations that is free for you to download and start modifying for your own practice. If you like this video, be sure to subscribe, because there's always more coming. If you're excited to incorporate Python into your own practice, I encourage you to enroll in my course, Python for Structural Engineers. In my own experience, structural engineers use Python in ways that are unique from programmers or data scientists. The difference is, we don't just do analysis, we do design and documentation. The course is offered throughout the year to a limited number of participants. I do intakes in different time zones. Go to structuralpython.com to learn more about the course, and also how you can enroll in a free mini course where I teach you a new method of doing design calculations using the open source libraries, handcalcs, and for all people. I look forward to seeing you.